we want to talk about specific types of reactions. Again, one type is that acid-base reaction. Sometimes it's also called neutralization reactions. And what we find is that acids are substances that produce protons. We've kind of alluded to them when we were naming them, and we're really not going to do much more than them, but notice it's an operational definition. So it has to have hydrogen in it, of course, because how are you going to produce hydrogen with a plus charge if you don't even have hydrogen? So it has to have hydrogen in it. We generally write the hydrogen first. But even more importantly, when it is placed in water, it dissociates to make the H plus ion. So that means that I know that all acids are going to be broken up into H plus and whatever the remaining anion is when they're placed in water, if I know it's an acid. And just to make it complicated, and it's just reality, it is what happens. As soon as that H plus is made, because it's being surrounded by water, it will bind to a water and make hydronium ion, H3O plus. So sometimes you see it written as H plus aqueous, sometimes you see it written as H3O plus aqueous, which is probably a little bit more accurate, but it's more confusing because it seems like it appeared out of nowhere. A base, on the other hand, is a substance that produces hydroxide polyatomic ions when it's placed in water. So same idea. It has to have a hydroxide in it if it's this type of base. You'll learn in 122 about other types of bases that don't necessarily have hydroxide ions in them, but we're going to take bases have hydroxide ions in them, and when they're placed in water, they dissociate and make a hydroxide ion by itself. It can also be defined as something that accepts protons. And that's another type of, there's even a third definition. So a generic acid or base reaction is then going to be acid makes H plus plus A minus. Again, I don't know what A is. Sometimes it's written HA, sometimes it's written HX. It's some other anion. And it's bonded together covalently, but it can dissociate and break that bond and make H plus and leave the extra electron with whatever is the remaining portion. We'll just call it A minus for now. And so we have the Arrhenius version, that's of a base, which is the type that it produces hydroxide ion, would mean I have something with a hydroxide, I put it in water, and it's going to make M plus, and the hydroxide ion will be produced. Also, the Bronsted-Lowry was the one, is this defined as being, it is a hydrogen acceptor. So probably it's going to be a negative ion, and it accepts the H plus and becomes HB. This would be another way of showing it generally. I could also note that if I were to write this as MOH plus H plus makes M plus plus water, I'm really taking this Bronsted-Lowry definition for this type. So that's another version I could use. So I have these general reactions. Regardless of which acid, regardless of which base, I can make it generic. We also talk about strong acids and base and weak acids and base. Again, you'll spend more time on this in Chem 122, but strong acids and strong bases are ones that fully dissociate in water. So I place it in water and it completely dissociates. All of the acid is now H plus ions and whatever the other one, HCl minus ions. So whereas a weak acid, and if weak strong base would be, like I put sodium hydroxide in water and all of it dissociates into sodium ions and OH minus. If I come as soon as I've dissolved it in water, there are no more NaOH molecules to be found. They've all been broken up. However, we can also have weak acids. Weak acids are one that only partially dissociate in water. So for instance, this hydrogen phosphate ion is an example of a weak acid. Some of the molecules remain intact, but some of them break apart and form H plus and the phosphate ion. So because only some of them dissociate, I only end up with some protons, some hydrogen plus ions, and that means it's only a weak acid. It doesn't all produce acid. So the fact that only some of them end up dissolving and dissociating means that we call it a weak acid. You could also have weak bases. Again, they only partially combine or associate with H plus. So how do you know? There's a list. There's a list of strong acids and a list of strong bases. And if it's an acid or a base and it's not on the strong list, then it's a weak one. So for strong bases, it's hydroxides of group 1 and group 2 metals. So these are the ones you got: lithium hydroxide, sodium hydroxide, potassium hydroxide. We see those a lot in the lab. And then there's a couple more: the magnesium hydroxide, calcium hydroxide, and strontium hydroxide. And then for our strong acids, there's 6 of them. There's 3 that are binary that just have 2 elements, and they're all halogens: iodic, hydrobromic, and hydrochloric. And then I have 3 oxo acids that have oxygen in them: perchloric, sulfuric, nitric. So it's like one of those 6, it's a strong acid, otherwise it's not. So what, again, just kind of showing you the difference between a strong acid and a weak acid visually. If I have a strong acid, so here's my HCl molecules. It begins life before I put it in water. It's a molecule. It's a covalent molecule. It's stuck together. But if I put them in water, all of them that I put in water dissociate into the H plus ions and the Cl minus ions. There's no intact molecules of HCl left. It's all dissociated. But this one is acetic acid. So this is showing you what acetic acid looks like. And here I see 1, 2, 3, 4 intact acetic acids. They might be dissolved, but they're not dissociating. And then one of them broke off and the H plus came off. And so this one is acting as an acid and it dissociated. All the others are not. That's what we mean by partially. It may not be 4 and 1, but most of them remain intact and do not dissociate, and a few of them will dissociate and make that H plus ion. So that's what we mean about the differences. This ends up being something about an electrolyte. If we talk about electrolyte or conducting electricity, notice this strong acid or base has a lot of ions in it. It can conduct a lot of electricity. These are not going to conduct very much electricity because they don't really have any ions in there, just a few. It might weakly conduct electricity, but not by very much. So this would be a strong electrolyte. A weak acid would be a weak electrolyte. Okay, so now let's react them. If I react an acid and a base, the net ionic equation of all neutralization reactions is the H plus from the acid and the hydroxide ion from the base make water. That's what we mean by neutralization. So it doesn't really matter which one. If you can recognize that from the molecular equation that I have an acid and a base reacting to make water, then I could go ahead and do the net ionic reaction. In this case, HA would be broken up into H plus and A minus. BOH would be broken up into B plus and OH minus. And then I have my water and my BA aqueous, but since this is aqueous, this would be B plus and A minus. The A minus and the B plus are spectator ions, and I'd end up with H plus OH minus makes water. And in these particular ones, we're using, acids and bases with ions in them that are just +1 and -1, but there could be subscripts. That's not necessarily important. The idea is that the acids would be composed of H and some other substance. So it might be H2SO4. So it could have 2 hydrogens. That's not something, so that we're going to use just like we were talking about with double displacement reactions. We'll use the charges to determine what the product should be. But here we're kind of focusing in on what are we going to end up with as a net ionic equation.